The paper delves into the implications of estimating heterogeneous treatment effects using machine learning methods in policymaking, with a focus on fairness concerns. It posits that standard AI fairness approaches developed for predictive machine learning are not universally applicable to all causal machine learning applications. The authors differentiate between indirect and direct decision-making scenarios, suggesting that policymaking is best viewed as a joint decision where the causal machine learning model has indirect influence. They propose a definition of fairness for this scenario, emphasizing the need for a model that provides the information a decision-maker requires to make a value judgment about just policy outcomes. The solution does not lie in traditional AI fairness adjustments, but rather in careful modeling and awareness of potential decision-making biases. The paper discusses the intersection of causal machine learning, (CML), and AI fairness in policymaking, focusing on the distinction between direct and indirect decision-making power. CML models are designed to understand data-generating processes, rather than making autonomous decisions. The authors argue that traditional AI fairness approaches may not be suitable for CML models with indirect decision-making power, as they require human judgment and value-based decisions. In contrast to direct decision-making models, which can be directly used to make decisions or inform policy learning models, indirect models inform human decision-makers through providing insights into the data-generating process. This paper highlights the potential for inscrutable CML models to lead to worse decisions due to automation bias, where decision-makers rely too heavily on complex algorithms without fully understanding their implications. The authors emphasize that fairness is not merely about mathematical rules but involves sophisticated value judgments. They contend that AI fairness should focus on epistemic concerns, which involve the evidence provided by analysis, rather than normative concerns, which relate to the effects of decisions made with this evidence. The paper also explores how businesses and nonprofit organizations could use CML methods for various purposes, such as healthcare treatment decisions, employee performance evaluations, and price discrimination. Causal machine learning amalgamates methodologies for estimating average treatment effects and heterogeneous treatment effects, with the causal forest emerging as a prominent approach for the latter. This method's efficacy stems from its components, which include double machine learning for confounding adjustment. In policy learning, the causal forest is applied to estimate heterogeneous treatment effects, enabling the identification of subgroups that respond differently to interventions. Double machine learning, a crucial aspect of the causal forest, entails two stages. Initially, a machine learning algorithm estimates the propensity score, which represents the probability of treatment assignment. Subsequently, another machine learning algorithm estimates the treatment effect, while controlling for the propensity score. This approach effectively addresses confounding variables, ensuring accurate estimates of heterogeneous treatment effects. The paper also delves into AI fairness, emphasizing the imperative of formal fairness rules to mitigate the potential real-world implications of biased models. AI fairness necessitates considering both adverse and beneficial outcomes in the real-world distribution. This is crucial, as models may inadvertently perpetuate existing inequalities or create new ones, underscoring the need for fairness metrics that account for these outcomes. By integrating the causal forest with AI fairness concepts, the paper provides a comprehensive framework for policy learning that acknowledges the complexity of real-world scenarios. This approach enables the identification of heterogeneous treatment effects, while ensuring fairness and equity in the application of machine learning models. The framework proposed by Mittelstadt et al. 2016 categorizes concerns around algorithmic decision-making into three distinct groups: epistemic, normative, and traceability concerns. Epistemic concerns revolve around problematic evidence generated by machine learning algorithms, encompassing inconclusive, inscrutable, and misguided evidence. Normative concerns, on the other hand, focus on the actual effects of decisions made based on algorithmic evidence, including unfair outcomes, transformative effects, and traceability. This paper primarily addresses unfair outcomes, which refer to biased outcomes of systems rather than just their outputs. The distinction between epistemic and normative concerns is crucial, as machine learning methods in government involve a joint human-machine decision-making process. Human decision-makers can intervene to mitigate normative concerns by considering values and a wide range of evidence. However, even with human intervention, models can still indirectly affect normative concerns due to epistemic issues. This underscores the importance of discussing fairness even in causal models with no direct decision-making power. The paper highlights the difference between direct and indirect power of AI systems. Predictive machine learning applications typically wield direct power, making decisions based on complex data. In contrast, causal models aim to provide insights into the data-generating process, supporting human decision-makers. While predictive models have direct power, causal models exert indirect power by shaping the information presented to decision-makers, which in turn influences their decisions. In the context of AI fairness, the system's ability to affect the world is mediated through a human decision-maker, making the agent ultimately a human, not an AI system. This distinction is crucial when discussing indirect power. Evaluation plays a key role in the public policy process, as illustrated by the policy cycle model by Althaus et al. 2018. The model identifies the Australian process but is broadly applicable to other jurisdictions. Evaluation is far removed from actual decision-making, identifying issues but not automatically feeding back into decisions. The 5 steps between evaluation and decision can be seen as the factors removing a causal ML model from direct power. In situations with direct power, an AI model bypasses or incorporates these steps into its algorithm, whereas in indirect power, the human decision-maker plays a crucial role. Indirect power lacks some of the fairness problems of direct power but brings its own set of challenges. There are 3 kinds of poor fairness outcomes that could eventuate from a joint decision between a human decision-maker and a causal model. The first outcome arises from poor modeling, where the effect is incorrectly identified based on observational data. This can be remedied by doing better causal modeling. The second outcome occurs when the model biases a human towards an unfair decision. The third outcome results from the human decision-maker introducing unfairness into the decision-making process. The policy cycle model highlights the importance of evaluation in identifying issues, but it is not automatically incorporated into decision-making. The authors of the research paper delve into the limitations of AI fairness solutions in addressing unfair outcomes in human decision-making processes that involve causal models. They contend that these solutions are not suitable for heterogeneous treatment effect, HTE, estimation, as they aim to equalize estimates between groups, whereas HTE models aim to uncover differences in treatment effects between groups. This distinction is crucial, as differences in HTE estimates by sensitive characteristics are essential in understanding how interventions affect marginalized groups and identifying areas for improvement. However, the authors identified 2 exceptions where AI fairness becomes useful: policy learning applications and situations where human decision-makers defer entirely to HTE estimating models, effectively giving them direct power over decision-making. In these cases, AI fairness approaches can help ensure equality across groups and policy eligibility. The authors propose a new conception of fairness in causal machine learning, where models have indirect power. They suggest that fairness should be evaluated based on whether the outcome of the model, in the form of a policy decision, is an unfair one. This raises the question of what exactly an unfair outcome is, which is difficult to define mathematically. Drawing on Mittelstadt et al. 2016, the authors argue that fairness is simply the outcome that best matches the decision-maker's value judgment as to what is fair. In essence, the authors argue that AI fairness solutions are not suitable for HTE estimation and that a new conception of fairness is needed for causal machine learning, one that focuses on the outcome of the model in the form of a policy decision rather than the model output itself. This new perspective emphasizes the importance of understanding how interventions affect different groups and highlights the need for a more nuanced approach to fairness in machine learning. In the context of heterogeneous treatment effects, HTE, estimation, discrimination can be valid, such as in positive discrimination policies, or unfair, arising from epistemic concerns that obscure the data-generating process, DGP, and hinder fair policy judgments. Fairness is considered a subjective definition for the decision-maker, beyond the scope of machine learning methods. The authors argue that epistemic concerns in causal machine learning methods can be attributed to poor causal identification and estimation, similar to parametric regression methods. The opacity of machine learning methods makes it essential to analyze these problems as critical AI fairness issues. HTE estimating models can result in automation bias and responsibility gaps. Automation bias occurs when humans overly defer to a technological tool due to a lack of understanding of its inner workings, leading to false confidence in its recommendations. Responsibility gaps arise from automation bias, resulting in a gap between the effects of an automated system and what is reasonably knowable about its behavior. The authors revisit 3 cases where indirectly powerful systems lead to unfair outcomes: poor causal modeling, shaping decisions due to model structure, and unfair decisions made intentionally by a decision maker. They focus on the first 2 cases, which involve epistemic concerns that cannot be diagnosed due to the black box nature of the model. Automation bias with HTE estimating causal machine learning (CML) methods can result in poor causal identification in models that emphasize differences in treatment effects, leading to unfair conditioning of programs. To address this, the authors propose that humans using such models for decisions and those training CML models must understand the limitations of their models, challenge models when needed, and know when to employ other methods. The authors also discuss the convenient identification of causal effects in high-dimensional data, which may encourage lazy identification strategies. They highlight the importance of testing and codifying the boundaries of causal machine learning to prevent misuse and bias in estimates. Notably, local centering, a best practice in causal forest DML orthogonalization, can still bias estimates if the model is poorly specified, even with robust instruments or fully randomized treatment assignment. Observational causal machine learning methods are increasingly debated, as they harbor potential biases and necessitate a thorough understanding of their limitations. These approaches can yield biased results, particularly when adjusting for post-treatment variables proves challenging. It is crucial to ensure that all variables are pre-treatment, but this can be difficult, especially with high-dimensional datasets. The identification of causal effects relies on nuisance models that partial out bias, requiring significant machine learning expertise. However, a competency gap exists between fitting supervised machine learning models and fitting ones that can effectively partial out bias. This disparity can be substantial, and the use of observational causal machine learning methods should be approached with caution. A substitution effect may occur, where easier methods are employed over more rigorous approaches, potentially leading to flawed conclusions. Therefore, it is essential to exercise prudence when applying these methods, acknowledging the potential for bias and the importance of nuanced understanding. The application of heterogeneous treatment effects estimation in policy decision-making raises critical concerns and limitations. Conditionalizing policy interventions based on HTE estimates may lead to indirect power conditioning, where decision-makers prioritize algorithmic outputs over justice considerations. A crucial distinction must be made. HTE estimates do not determine whether an individual deserves a treatment, as treatment effects provide no insight into distributive justice. Moreover, if those who are worse off in a society exhibit lower treatment effects, this should not justify reduced intervention. The conflation of empirical questions with distributive justice concerns is a significant risk, potentially resulting in unfair targeting in policy decisions. This highlights the need for policymakers to carefully consider the ethical implications of relying on HTE estimates, ensuring that justice and fairness remain paramount in decision-making processes. In policy evaluation, heterogeneous treatment effect (HTE) estimation models are widely used, but their limitations must be acknowledged, particularly in the context of distributive justice. Over-reliance on HTE estimates can lead to automation bias, where decision-makers prioritize quantitative judgments over issues of justice, resulting in unfair outcomes. This is particularly concerning when HTE estimates are used to determine eligibility for programs, as they may perpetuate biases and unfairness. It is essential to consider human judgments and values in decision-making, rather than solely relying on quantitative estimates. The authors caution against using HTE estimates as the sole basis for eligibility decisions, as this can lead to unfair outcomes. Furthermore, the use of HTE estimating models poses potential risks, including the hiding behind the computer effect, where policymakers may use complex models to avoid personal responsibility for decisions. The novelty of these methods means that there is a lack of experience and established best practice, which can exacerbate unfairness. While HTE estimation with causal machine learning methods is a powerful tool for policy evaluation, it is crucial to understand the fairness implications of these methods before using them for decision-making. The authors acknowledge that their discussion is not exhaustive, and there may be other harms and benefits that have not been addressed. Nonetheless, they emphasize the need for a critical discussion of causal machine learning methods and their potential implications for fairness and justice in policy evaluation. By recognizing the limitations and risks of HTE estimation models, policymakers can work towards more equitable and just decision-making processes. The research emphasizes the significance of considering confounding variables and the need for robust methodologies to ensure unbiased policy decisions. It highlights the works of Athey and Wager, who propose policy learning with observational data, and Chernozhukov et al., who discuss double, Debiased machine learning for treatment and structural parameters. The concept of causal forests and their applications in policy evaluation are also discussed. Evaluating the effectiveness of policy interventions relies heavily on accurate assessments of treatment heterogeneity, which refers to the varying impacts of a policy on different subgroups within a population. Recent research has underscored the importance of considering these heterogeneous treatment effects in policy evaluation, particularly in the context of electricity conservation and household energy use. One approach to addressing this challenge is through the application of causal machine learning, which enables the estimation of treatment effects while accounting for confounding variables and biases. By leveraging these methods, policymakers can better understand how different demographics respond to policy interventions, ultimately informing more targeted and effective decision-making. However, the development and deployment of AI systems in the public sector also raise critical concerns around ethical governance. It is essential to ensure that these systems are transparent, accountable, and unbiased, lest they perpetuate existing social inequalities. In this regard, the development of interpretable and unbiased machine learning models is crucial. By providing insights into the decision-making processes of AI systems, these models can facilitate more informed policy decisions and enhance accountability. Ultimately, the integration of statistical criteria of algorithmic fairness, treatment heterogeneity, and causal machine learning is critical for effective and equitable policymaking in the public sector. This video explores a range of research papers and technical reports, delving into key topics such as the evaluation of government spending, multi-treatment uplift modeling, causality, and artificial intelligence. A central theme is the importance of unbiased decision-making and the need for transparent AI systems that can be understood and trusted. One significant concept discussed is heterogeneous treatment effects, which refers to the varying impacts of different treatments or interventions on different individuals or groups. This concept is crucial in policy learning, where the goal is to understand how various policies might affect different segments of society. The research also emphasizes the importance of understanding causality, the relationship between cause and effect, in order to make informed decisions. In the context of AI, this means developing systems that can not only predict outcomes but also explain why those outcomes occur. Multi-treatment uplift modeling is another critical area of study, as it allows researchers to evaluate the effectiveness of multiple interventions simultaneously. This approach is particularly useful in evaluating government spending, where policymakers need to consider the potential outcomes of various programs and allocate resources accordingly. Throughout these discussions, the importance of transparency and explainability in AI systems emerges as a recurring theme. As AI becomes increasingly integrated into decision-making processes, it is essential that these systems are designed with transparency and accountability in mind, ensuring that their outputs are not only accurate but also understandable and justifiable. In summary, this video provides an overview of cutting-edge research in AI, policy evaluation, and decision-making, highlighting the need for unbiased, transparent, and explainable AI systems capable of understanding and predicting complex outcomes.